Okay. So I'll be brief on the announcements because this is your time to shine today. This is our review for Exam 2. I think we're up to date on grades except for homework 4.2, which we're still grading. Homework 4.3, what I'm going to do is release the solution tomorrow and give you all time to review and study. Okay, so what I'm going to do is go through a few items in our exam review slides, and then it's open to you in terms of questions. So did I open that? Yes, okay. All right. All right, so I'll say this in terms of format. The format on this exam is identical to what you had on the last exam. Like, it's not suddenly going to be multiple choice, or it's not suddenly going to be, 7 problems. I mean, like, problem 1 was a series of conceptual questions, and then there was workout, computationally based problems. Same format. I'm not trying to mix that up on you. I put on here, and I typically always put on here that a straight edge will probably help, but honestly, I don't know that it would matter all that much. It will definitely help on exam 3, though, having like a straight edge or something to draw straight lines and whatnot. Same thing with the formula sheet, same rule. I don't want to belabor this because I want to give you all time to ask questions and whatnot. But same story. I don't care if you snip something out of the slides here and there. Just make the formula sheet yourself, and then you'll turn it in. I'll give it back to you and all that. By the way, I let you all make formula sheets for all the exams, and then for the final, I just sort of spot check it that day, and I let you take it with you. So because I know that sometimes those formula sheets like you end up referring to them a lot later, so I don't want to keep it. You'll get it back. Okay. Here's what's on the exam. Rigid body systems, rigid body equilibrium. Okay, so for rigid body systems, I think it's prudent to just sort of mention you need to have the ability to compute a dot and cross product. I would say that we probably agree that cross products are more important for what we do in this class, but you do need to be able to do both, although dot products are pretty easy. Be able to compute moments. So we have what I would call our general definition, our R cross F, or the magnitude of a moment times its moment arm. The magnitude of a moment equals the magnitude of the force times its moment arm. So either the traditional R cross F format or just the magnitude being force times distance, I think are valid for the exam. Moments about an arbitrary axis would be the cross product of R and F, and then take that cross product and dot it with lambda, the lambda being the unit vector along the axis in question. Okay? Be able to resolve force couples. So that's, if you have two 20-pound forces that are parallel opposite directions separated by 6 feet, take that 20-pound force couple and replace it with a 120-pound moment, because that's what that is. And then really all those tasks are leading to the first real big topic on this exam, which is being able to generate equivalent force systems. Being able to take a system of a bunch of forces and replacing them with a smaller system. Okay? Rigid body equilibrium, that's reactions. There's nothing really else to say about it, just being able to compute support reactions in 2D and 3D. Okay, let's talk about like the greatest hits of what's on the exam. So first off, cross products. Remember that the cross product of two vectors, if I have vector A and B, our definition for the cross product was that the cross product of A and B is a vector. The vector has a magnitude that is equal to the area of the parallelogram formed by A and B, and that its direction is normal to that plane. We can also evaluate the magnitude of a cross product by AB sine theta. Okay, the magnitude of A, the magnitude of B, and the sine of the angle between them. We never really use that though in practice, because really what we're doing in practice is this. There's two ways of doing it: the rule of Saris or cofactor expansion. For the purposes of the problems that you're doing on the exam, I don't care which one you use. Like whatever. I think that by the time we start teaching this, like I use this method because I think it's easier from a bookkeeping standpoint to get your positives and negatives accurate. But I also would understand why some of you would like to do this. I don't care which one you do. You do whatever one you want. So whatever's comfortable to you. The dot product, remember the dot product of two vectors yields a scalar. The magnitude of each vector is the product there, and then, or the product, magnitude, and then if the cross product is related to the sine, the dot product is related to the cosine. So just a pure dot product application is being able to form or compute the angle between two vectors. I think it's a really easy way of doing it. The formal definition of a moment is r cross f. R being the position vector measured from the point wherever you're taking the moments to the line of action of f. Okay. We do r cross f first because remember that animation with the parallelogram? If the force remains constant, but you keep changing that position vector, you still get the same area of the parallelogram. So that's why we do r cross f and not f cross r. We can also represent the magnitude of the moment as either just the magnitude of the cross product or just FD. FD being the magnitude of the force times the moment arm. And the moment arm is the shortest distance from our point in question to the line of action. Either one is fine. If we can take our general definition for moments in 3D and sort of simplify it or resolve it into a formal or into a definition of moments in 2D. Remember, if you have forces and distances in 2 dimensions, if you restrict everything to a single plane, then the moments are all going to be normal to that plane. So if your forces and position vectors are in x and y, then your moments are in z. Okay, so that's why the moment vector in 2D is always just some quantity times k, which is a lot of times why when we're doing 2D problems, we sort of dispense with the IJK notation because we know about which axis the moments are going to be rotating. So we just don't worry about it. If we're computing moments about an arbitrary axis, we'll just take r cross f and dot it with the lambda vector that defines that axis, because a dot product, another application of a dot product is projection of a vector upon an axis. So if you have a vector and you dot it with a lambda vector for an axis, you figure out how much of that vector is projected onto that axis, which is why if you just dot lambda with r cross f, you'll get the moment about that axis. And you can do this separately and then dot, or you can throw it all in one big determinant. Either one's fine, you get the same answer. Okay? Oh, and lambda starts anywhere along the line of axis or along the axis in question and ends anywhere along the line of action. So you got multiple options there. My advice, if you ever have to do that, is do the easiest one. Whichever one yields the most, and really, like, your favorite number on this exam should be 0. Any time that you can throw 0 into a cross product makes the math a lot easier. Okay. Force couples, same magnitude, opposite direction, parallel lines of action. We can replace a pair of forces in this fashion with just a single moment vector, and that moment vector is just going to be the r cross f, and r being from one line of action to another line of action. Equivalent systems. So this is when we take system 1 and system 2, and really the easiest way of equating system 1 and system 2 is to just sum up the forces in system 1 and say that resultant force vector is the single force vector in system 2, and the same thing with the moments. The big thing to keep in mind is there is a difference between an equivalent system of forces problem and an equilibrium problem. In an equilibrium problem, we are summing the forces and moments and setting those sums equal to 0. Because what we're interested in an equilibrium problem is figuring out what are the magical values of these unknowns to keep the system in equilibrium, to figure out that sum. Like in an equivalent systems problem, you're just adding them up. Okay? So equivalent systems, just add them up. Equilibrium, add them up, set them equal to 0, solve for your unknowns. Okay, that's the difference. Okay, everybody okay with that? All right. For static equilibrium in 2D, we have 3 equations of equilibrium. For static equilibrium in 3D, we have 6 equations of equilibrium. What I will tell you is 2 things. I will say this right off the bat. The first is that I am not interested in giving you a problem on this exam that takes 7 hours to do. That is not the case. I told you a while back that I use a rule of 3, that if I could do the exam in 20 minutes, you could do the exam in 60 minutes. I have done this exam. It is a surprisingly quick exam. It is not time sensitive, okay? So it's not going to be homework. It's not going to be 3 homework 4.3 problems. Not the case, okay? I'm just telling you right now, it's not that, okay? And the other thing I'll tell you is I am not trying to get you worked up on this. I am not going to use some, you know, strange boundary condition with like forces here but no forces here and then a spring there. It's not that. This is, I mean, this is an introductory statics course, so the stuff that you're going to see on a problem in terms of boundary conditions is stuff we have dealt with before. I'm not going to throw something at you that you haven't seen before in that regards. I don't think that it really tests your ability as an engineer anyways, okay? Sound good? The floor is yours. Any questions that you have, any concerns that you have, any doubts that you have about this exam, it is your turn to shine. And if you are worried about the exam, I want to see if I can assuage those concerns. So the floor is yours. Everybody just tired? Y'all look, yeah. We're over halfway through the semester. But yay. We're still here though. It's like, yeah, when Frodo was taking the ring to Mordor, it didn't get easier. It just got worse. The back half of the journey was a lot easier. I get it. All right. Any questions at all about any of this?
What do you foresee being the most missed area on the exam?
Oh, that's a good question. What do I foresee being the most missed area on the exam? All right. I will give you 2 answers. Sorry, that was funny. I mean this when I say this. The first answer is not reading the problem and answering the problem, okay? I have seen exams like this where you see the problem and suddenly you find yourself doing more calculations and more work than is necessary, okay? If you're asked a question and you need to find this, don't do the whole thing. So an example, homework 4.3, okay? Let's say that was a long homework. I think we would all agree, right? Okay, what if I gave you a problem like homework 4.3 and all I asked was write this force vector, right? So all you would have to do, take a distance, turn it into distance vector, turn it into a unit vector, multiply it by a magnitude. That's it, right? And then you're writing R vectors and cross products and doing all this, and suddenly you are spending way too much time doing work that wasn't necessary, okay? So the first thing that to answer to my first answer, to directly answer your question, I think the first thing that will trip people up is people not actually responding to the questions.
Just falling into the habit of finding everything.
Yeah, you're like, well, this is what we've been doing, so actually read the question and answer the question. That's the first thing. The second thing also goes into reading the problem. All right, let me give you an example, again, as related to homework 4.3. Homework 4.3 was very much like a homework that an example problem that we did in class, where here's the problem, do it, right? Now, what if on homework 4.3 I said, here's the homework, but by the way, here's the answer for 2 of the cross products. Next thing you know, you're evaluating every single cross product, but you just missed the fact that I gave you 1 of them or gave you 2 of them, right? So because these problems are so long, I might give you some information to make the calculations shorter, okay? Pay attention is what I would say. Because what I don't want you to do is waste time on that. If I've given you one of the values, given you one of the data points. Those are the two things that I think would cause the biggest issue, is just responding to a bunch of nonsense that has nothing to do with what the problem's actually asking, and not realizing that you may have been given hints. You may have been given intermediate values, and you don't need to evaluate all that. That's my answer. I hope that answered the question. Oh, I'll give you a third answer. Positives and negatives. Flipping signs. That'll happen. That's just going to happen. Point blank. You know, like, I mean, we were doing it in class where we had like a negative of a subtraction, and then the subtraction was negative, so we had like a negative, then to a positive, then back to a negative, stuff like that. I don't think it'll be a big deal, but I think that everybody is capable of just doing that. It's not a big deal. It's not the end of the world. But I mean, if the answer's wrong, the answer's wrong. You know, so it'll be a deduction, but it won't be, oh, you flipped a negative, F. It's like that Parks and Rec scene, like, oh, positive, negative, jail. Straight to jail.
Singing too loud in public?
What's that?
Singing too loud in public?
So that's fine. That was a good question. You got me thinking on that one. So yeah, I don't think that the exam is as computationally as intense as you might think it is. I actually think it's a little light on that regard. As light as it can be, given the subject matter. So yes?
What would be some good conceptual things to study?
Good conceptual things. That's a good question. That's a fair question. So I would go through just like basic definitions. So if I threw out for example, a good conceptual question might be like, what does it mean for two systems to be equivalent? What is, you know, well, I actually mentioned one just now, like, which would be a better, so like, here's a conceptual question. If I asked you to find the angle between two vectors, you could find that using either the dot product or the cross product, but which would make more sense? Probably the dot product, because it's less calcs, you know what I mean? Stuff like that. But I would say definitions, making sure that you understand, you know, we've defined boundary conditions, we've defined terms. There aren't a lot of them, and I would say that the other thing I'll point out about the conceptual problems is much like with the computational problems, make sure and read them before you answer them, okay? Like, explicitly read them. I don't want to say much more than that. I don't want to say much more than that. But there aren't many of them, and I don't think they're incredibly challenging. But if you understand the definitions and you read them, I think you'll do just fine. Yes.
Based on previous classes, what is usually the problem topic?
Based on the last time I've done this type of exam, what's the problem topic? I'm going to give you an answer that you might not expect. You'd be surprised how, I've been surprised that there's been scenarios where students have had more problems with 2D problems than 3D problems. That they actually see the 3D problems as pretty straightforward. But then they get to the 2D problem, and suddenly it's more challenging. When it really isn't, you know?
Yeah.
That's a good question. Yes?
Can I ask what the average was on exam 2 previously?
Oh, I don't remember offhand, but it's it was typically a little lower than exam one, but not from a 70 to a 40. Like we're talking, I think the last time I taught this class, we're talking maybe 78 to 72, like high 70s to low 70s, but not below that. I'll be honest, I mean, I'm not trying to say this like I don't mean this to be a flex, but I don't really have very many exams I can remember. I don't often have exams that are like that bad, you know, so I'd like to think I don't, so. I'm not saying that like every person's gonna get 100, but let me put it like this. If I am the type of professor that if I give an exam and everybody in the class gets a 30, I find that to be more of a problem with me than you, okay? I mean that. That means I did something wrong, okay? I'll actually tell a story about this. So I genuinely think that the most difficult class I teach is Engineering 216, Mechanics of the Materials, Mechanics of the Formal Bodies. I think it's the hardest class I teach. When we were coming out of the hills of the pandemic, so I went from, you know, fully virtual teaching by myself in my office for a year to a camera to, you know, the in class, everybody wearing the mask, to sort of transitioning back to normal where we are now. And so I made a decision that for that first sort of like semester that we were back, I would allow open book exams. And my main reason for doing that was that I thought that the year prior, a lot of the foundational courses in engineering and science and what have you, everybody was, you know, taking in their living room in their PJs. And so now they're coming in here and having to do cross products and calculus and so on and so forth. And so my thought was, I'll ease everybody into like a standard way of doing things. So I said for that first, you know, set of exams, we'll do open book. So sort of like ease everybody back into it. And for a little while, that was fine. Then I taught Engineering 216, and the first exam was really bad, okay? And I really was taking a look at it, and I was looking at the homeworks, looking at the, you know, the exam grades, and I think what happened was everybody, and I told the class this, I said, I think what happened was everybody said, I don't have to worry about studying because I have an open book exam. So I'll just go in. But Engineering 216, it was a difficult class. So the class as a whole didn't do very well. So when that happened, the exam average was pretty bad. It was like in the 50s. And I said, here's what we're gonna do. So we did like exam corrections. So we allowed everybody to like, you know, sort of give them the exam. They sort of redo the problems, turn them in. I took the average. I said, we'll move past this. But then the next exam, closed book, no open book. Now here's the funny thing. The second exam, in my opinion, was harder than the first. The class did 20 points average better because they had to actually do it. Now I'm sure that class hated me because, you know, they lost their closed book exams. When I walked in, I said, look what happened, you know, you all did fantastic. So in that exam traditionally, I had gotten very low averages, and the average was close to an 80. So it was like 77 or something. So yeah. But my overall point to the story is when I got an average that was that low, for one, we addressed it, but I treated it more as like there's something that I was doing wrong as opposed to something you all did wrong. Like if we have an exam and everybody passes it but 5 students or something, the exam was probably fine. But if 60–70% of the class fails it, that's probably a problem with me, and we need to correct that. That's my attitude about things. So that's how I've always operated. So I am not in the business of coming in here and saying, hey everybody, here's your 40% average, let's move on. That doesn't do any good. So one corollary to that. So if you plan on taking the FE exam, this is how the FE exam is kind of graded. Like, I say kind of because there's a lot of like really complex statistics that goes in the background. But the idea is there's like a question bank, and if 87% of the country misses question 5, there's probably something wrong with question 5 more than there is with 87% of the country. You know what I mean? So that's taken into account. At least it was when they did the paper-based exams. I think now it's probably even more complicated because of question banks and all that, alternative question types. Yeah. Statistical magic that's way above my head. So. Did that answer everybody's question, hopefully? Did that make everybody feel a little better? Okay. All right. Any other questions? This is good stuff. I'm getting good questions. I like these questions, by the way. This is good stuff. Yes?
If you were making a formula sheet for this, how would you structure it? Would it be like a step-by-step thing, or?
That's probably not a bad idea for certain types of problems, but I would not handcuff yourself to a specific class of problems, okay? In other words, I'm not trying to trick you on the exam, but I may ask you something that's just, here's a problem, answer this, you know, that fully explores the skills that you've learned here that isn't outside the scope, but it might be different. And I don't want you to structure your formula sheet that, well, it didn't fit in this little box. What do I do? You know, this is, I mean, very much an add, subtract, multiply, and divide exam. I'm not really trying to trick you, but I may challenge you, you know. And what I don't want you to do is box yourself in. So I think some procedures are fine for certain things, with the understanding that if you get asked something a little bit outside the box, that you can handle it. So some basic formulaic definitions, some terminology, some basic procedures, probably not a bad idea. And what I'm talking about when it comes to these outside of the box questions, I'm not talking about the gross majority of the exam. I'm just saying that, you know, I just don't want you to box yourself in. Especially if I give you a problem and then I give you a value. I mean, I've had students who, because of that, because of exactly what you're talking about, do exactly what I warned you at the beginning. They start doing the whole problem, and they had answered the problem 20 minutes ago. You know? That's fine. Yes?
So kind of going like what off he said and even what you said, do you think it would be a waste of time to put on the formula sheet, kind of like a step-by-step of how to do something like homework 4.3, you're just using like ones and zeros?
I don't think that's a bad idea. I don't have a problem with you doing that. It's a fine idea. And if anything, it forces you to like formulate the process in your head. I think that's a valuable exercise, and I would do that for, and I would recommend that for anybody. I just don't want you to box yourself in, you know, with that.
So like if one of the questions was like what you said, like find the force vectors, I wouldn't just put on my formula sheet like just up to the force vector, because what if it was like something after?
Exactly, yeah. Or here's an example. Here's a perfect example of what I'm talking about. The last exam, the third problem, like there was the conceptual problem, the third problem. That problem, I gave you I gave you a bunch of 3D force vectors, and I said, give me the magnitude of the resultant and give me the direction cosines. Now, we've done that problems like that in class, and it involved distance vectors, lambda vectors, force vector, distance, lambda, force, distance, lambda, force. I gave you the forces, right? All you needed to do on that problem was add up the vectors, Pythagorean theorem for the magnitude, divide by the magnitude to get a lambda for the resultant, inverse cosines. That's all you needed to do. So I started you halfway in. You know what I mean? Wasn't trying to trick you. If anything, like I told you on that exam, that I was trying to take the three-dimensional confusion out of the problem for that exam. And I think I did by just saying, okay, all that hullabaloo that you got to do to get to the force vectors, here's the force vectors. Now do something with them. But I imagine that for some of you, it tripped you up because we had never done a problem where you started in the middle. That's sort of what I'm getting at. So, does that make sense, everybody? Okay. I sort of said something in that response that I feel may trigger a question. And I mentioned this before. There is a little bit of 3D on on this exam. But I will say, I think it is very manageable in terms of how it's presented. In terms of the images, descriptions, I don't think it's complicated. I don't want to say any more than that, but I don't, like, if you're one, the schematics that are presented, I really tried to take care to ensure that there were no optical illusions, you know, where, like, is it a 4 or a 7, or, you know, is it this way or that way? I think it's pretty straightforward. So, doesn't mean you don't have to be able to see things in 3D, but I'm not trying to turn the exam into a kaleidoscope. So, if that makes sense. So. Does everybody feel better about the exam or worse? I'm curious. Any other questions? Feeling better? All right. Hold on. Going once. Going twice. Okay, a couple more logistical items. So, like last time, I teach in this room right before class. So, like, I'm probably going to end my structures class a little bit on the early side so that we all can start. So everybody's here, like, I mean, we'll start early, but at a minimum, we'll start right at 11 o'clock on the dot. One of the things I did do with the format of the exam is there should be ample room on the exam to do all the math and the calcs. You should have ample space to do that. So just come in with the calculator, with pencil, formula sheet, get to work. We'll go until 11:55. Okay. I would go long. I would have no problem going until 12. It's just we have a class coming in. So, sound good? All right. We'll see you on Friday.